Good morning, everyone. So my name is Vincent, and I'm a PhD student working at LAM and Columbia University in galaxy evolution and instrumentation. So for instrumentation, as much as for galaxy evolution, I had to go through a lot of image processing. Then today I'm going to introduce you a side project which emerged from this time spent processing images. I will try to convince you that plugins are an amazing opportunity to address the issue of image processing, which is a pretty complex task to handle. As I'm not a software engineer or anything, I might say stupid things at some point. So if I do, don't worry, you will have time to correct me at the end. So I feel that what is image processing is not even that clear. It's more like a continuum that goes from basic visualization, like zooming, panning, scaling, that are handled very efficiently by all PIDs viewers, to enhanced visualization, which begins to become standard in modern speed viewers with like 3 or 4D visualization, profiles, catalog overlay, and so on. Then with image analysis, which is different from the above, as it does not only bring qualitative, but also quantitative information. And I only know a couple of applications that address this issue. And then image processing, where we actually change the pixel values for background subtraction, stacking, or other things, and down to research-grade pipeline, where all the above processing can be generalized to an infinite number of images. And of course, as you can imagine, the deeper we go in this processing, the less it is included in current astronomical imaging application. So still, I will try to give some hints about why we need to address this issue, what are the challenges that future image processing applications need to tackle, and why I think that plugins represent a good opportunity to address these challenges. And I will then present an attempt to design such a plugin. So astronomy is a particular discipline where an essential part of the job relies on image analysis. And it's in addition evolving towards James Gray's force paradigm, basically stating that after science discoveries being driven by empirical evidences, scientific theory, and computational science, now the science undergo force paradigm shift, where discoveries will be mainly driven by data-intensive work. And for science relying on image analysis, processing software must be much more available than what it is right now for the scientific community. And the community that codes, but also the one that does not. Currently, even basic processing, like doing a radial or energy profile or cropping an image with WCS, needs to be recoded, which is extremely time consuming. So I sent a small survey to lead developers to verify that indeed a small number of apps were allowing such processing, with I think the most complete work in this sense being Gaia from the Starlink project. So image processing is a science-driven, and the needs evolve and differ depending on the science, instrument, and energy domain people work on. And I feel this draws a new challenge for current and future imaging software, which is mimicking what has been done in bioimage software by really addressing image processing. And of course, this is a too complex task to handle for only one full-time equivalent, as we can see here for the different applications. So how do we do it so that it is the most beneficial as possible? Image processing applications will need at some point to allow the entire succession of processing, all the way down from visualization to image analysis and research-grade processing. Second, as all PIDs viewers converge toward high interactivity, processing software need to keep the same consensual feature of interactivity with regions, profiles, plots, and so on. And again, as the needs differ on the type of science you do, and evolve with time, future applications need really to catalyze community collaboration and code enhancement so that it is easier to follow the evolution of the needs. It's time, I think, to aggregate the processing tools developed by different teams around the world and aggregate them wisely as it is done in other fields already. Of course, all these challenges cannot be faced by one full-time equivalent. And for instance, DS9 lead developer confessed that spending on 80% of its time supporting users on maintaining existing things, which gives him only 20% of time to innovate and add new features. So how do we do? I feel the best way of tackling the need of image processing is by boosting or encouraging collaborative development. In particular, let me explain why I feel plugins for PIDS viewers applications are an exciting compromise. First, it allows significant and free innovation without breaking the software integrity. In addition, plugins would lean on already proven PIDS viewers that are stable and easy to use, and then they can take advantage of the already here high interactivity. We have the chance to be in a field where collaborative development is the standard, so let's take advantage of it. There are too many PhD students, even me, recording existing things, and also algorithms that sink into oblivion each time a PhD student leaves or a senior researcher retires. And it's not a coincidence if a major part of the top 10 of fast-growing open source apps are following this implementation approach. It's because it works. And then, of course, you would say that it's already done in several astronomy tools, and that's true. That's a good thing. And I think we should encourage it even more. We should ask ourselves how to do it efficiently and reproduce existing initiatives that work in other fields. In this vein, I have tried to gather some processing I used and create this kind of plugin, a plugin that tries to answer the three challenges that I described before, and also gather a glimpse of all the possibilities that offer PIDS viewers extensibilities, so that it motivates astronomers exploring this development approach. So I decided to use the PIDS viewer DS9 for three main reasons. First, because its 30 years of development has made it extremely stable, and that they always follow the rule, keep it simple. Second, they are the most popular in SAOImage visualization with Aladin, which has a slightly different purpose, and also because they allow simple Python extensibility. And then it's easy to understand why I chose Python, despite the fact that I'm lazy. First, to take advantage of the great synergy around it, because it is easy to code, read, reuse, and so on, and that the existing packages like matplotlib or astropy and others allow to implement really easily an infinity of processing codes. So the goal of pyds9 plugin is to take advantage of visualization application to push it a step further by allowing to analyze image while keeping a high level of interactivity. The processing functions can then be generalized automatically to a set of images to turn the quicklook tool into a real multiprocessing pipeline. So I'll just show a video about how it works so that you can see. Let's open an image with DS9. We explain the interaction by the way we use metadata, like regions, plots, catalogs, to improve the communication between the user and the data. For instance, by a simple key hit, you can explore the dynamic of a dark region by computing and applying scale thresholds computed on the encircled regions. If you want to explore the dynamic of the full image, just unselect the region and rerun the analysis. To get a better sense of what is in your image, the same region can be used to visualize in 3D the encircled area. By using the visualization toolkit, you get a state-of-the-art 3D rendering with the possibility to add contours, change the scale, and create animated GIFs. These can also be very helpful for 3D cubes or multi-band images. This plugin incorporates essential functions to support instrumentation or analyze the performance of your data. For instance, by encircling a bright and compact object, you can compute a radial and energy profile. Every DS9 plot, profiles, histograms can then be fitted by different functions, with the possibility to add a high number of spectral features. The user can then change the initial guess parameters to be sure that the fit converges. We added a Python interpreter to have the possibility to run direct transformation or analysis on DS9 images. In one line, you can create artificial images, crop the DS9 image, mask high values or add noise, for instance. The result will automatically be loaded in DS9. To see the command sent by DS9, just select the analysis command log in the analysis menu. As one line is not enough, we added the possibility to link any Python macro so that people can add their own transformations or analysis in a simple language. The possibilities are then infinite. You can implement and run models, link an artifact detection code, run complex transformations or analysis. The key aspect of all the processing functions is that they can be applied to an infinite number of images by adding to the DS9 command the path of a set of images by using regular expression. This will literally turn your macro into a real multiprocessing pipeline. You can also specify the number of processors you want to use. We also linked the most famous astronomical software to the plugin to allow research-grade analysis on processing. For instance, you can easily optimize a high number of Sextractor parameters by using it with DS9. You can then interactively select the sources, verify their magnitudes, filter, and order them. Once again, when you found your best set of parameters, you can turn it into a multiprocessing pipeline and launch the command on a set of images. Extracted sources of all the images will then be saved in a second. This versatile Python plugin is designed from the ground up to perform research-grade interactive processing of images and to allow scientists to develop their own macro and turn them into important pipelines. Okay, so to conclude, let's combine, I think, the plugin approach with popular scientific programming language to explore the full capability of community-driven image processing. And I think that on the developer side, it's not that hard to do, and there are plenty of interesting examples that worked. And generating the enthusiasm on the synergy might take some more time, so that's why I think that we need to address this issue quickly. So if you have any question or remark, I would be happy to hear them or to talk longer after this session. Thanks for listening.